Today I will be presenting the project titled Generative AI Honey Token Factory with Attack Detection and Report Generation. This project was developed by Kritika A and Medika A under the guidance of Gayatri Ma'am, Assistant Professor in CS Department. The domain covers cybersecurity networks and machine learning. Without further delay, let's get into it. Modern enterprise systems heavily rely on API keys, access tokens, and configuration secrets to function. But those credentials are constantly at risk. They get exposed through misconfiguration, insider misuse, source code leaks, phishing attacks, or malware. Now, the existing solution for this is honey tokens, fake credentials planted to trap attackers. But the problem is traditional honey tokens are completely static and predictable. A sophisticated attacker can easily identify them and simply bypass them. On top of that, existing systems don't provide any real-time visualization of credential misuse or automated behavior-based analysis. So what we truly need is an intelligent automated framework that dynamically generates realistic honey tokens, safely embeds them in the system, instantly detects unauthorized usage, visualizes attacker movement through graph techniques, and generates structured breach reports. That is precisely what this project delivers. Traditional security mechanisms like static honey tokens and rule-based intrusion detection systems are reactive by nature. Our project proposes a generative AI-based honey token factory that proactively creates realistic fake credentials, including database credentials, API keys, tokens, based on observed user behavior patterns. When an attacker accesses or misuses one of these honey tokens, the system identifies the activity in real time through continuous log monitoring and graph-based anomaly detection. It then provides live breach visualization and automatically generates detailed forensic reports to support faster incident response and investigation. Let me walk you through why this project is necessary. Rising credential-based attacks, the number of cyber attacks involving stolen API keys and access tokens is rapidly increasing. Second, lack of intelligent deception systems. Existing honey token systems are static and predictable. Third, integration of AI with cyber deception. Combining generative AI with security significantly enhances the realism and adaptability of honey tokens. And fourth, real-time breach detection using graph analysis. Graph-based models help us visualize exactly how an attacker moves within a system, improving our understanding of attack patterns and risk levels in real time. We studied 7 key research papers to build the foundation for this project. Paper 1 by Prabhakar focused on generating and deploying honey tokens within relational database. They showed that properly crafted honey tokens can effectively expose malicious queries while maintaining low system overhead. Paper 2 introduced H44, a software-defined deception framework using SDN to orchestrate deceptive assets dynamically. However, it faced scalability issues under high-volume attacks. Paper 3 provided a comprehensive survey of cyber deception techniques, including honeypots, decay services, and deceptive network topologies, analyzing how dynamic response generation improves honeypot realism. Paper 4 proposed multidimensional few-shot data generation to synthesize high-quality malicious variants, significantly boosting intrusion detection performance in low-resource datasets. Paper 5 and 6 explored blockchain-based and federated learning-based intrusion detection for IoT environments, offering strong detection accuracy but limited to specific device ecosystem. Paper 7 Graph-fed AI combine federated learning with graph-based AI to detect DDoS attacks in IoT systems. This directly inspired our graph intelligent modules. Each of this work contributed to shaping the specific component of our proposed system. Let's look at the issues and challenges we addressed. Traditional honey tokens are static and predictable, making them easy to spot and bypass. Most security systems are reactive, detecting threats only after the system has already been compromised. And existing tools lack real-time tracking, visualization, and proper SIEM integration for credential misuse detection. The challenges were equally significant, generating realistic, context-aware honey tokens without overlapping with real credentials and effectively processing large-scale logs while implementing graph-based anomaly detection, all without adding performance overhead to the system. Our solution is a generative deception-based security architecture that decomposes credential protection into multiple intelligent computational stages. Module 1 is Generative Honey Token Factory, which uses a diffusion module combined with variational autoencoder. Module 2 is Attack Behavior Graph Intelligent Modules, which uses a temporal graph neural network to model and detect attacker movement patterns over time. Module 3 is the Adaptive Honey Token Deployment Engine, which uses multi-agent deep reinforcement learning with the SAC algorithm. Module 4 is the Threat Attribution Engine, an attack profiling module which uses a heterogeneous graph transformer combined with graph sequence modeling. So this is our architecture. Looking at the overall architecture, which we have named HoneyGuard, the flow begins with a honey token factory generating tokens using VAE and diffusion modules. These tokens are then deployed through the deployment engine into .env files and trap endpoints. When an attacker accesses a trap API key, an alert is immediately triggered. The system then runs attacker's behavior graph intelligence, performs attack profiling, generates reports, conducts geolocation based attack detection, and feeds into the prevention model, which blocks malicious IP and continues observing attacker behavior for further analysis. System requirements for hardware. The system requires an Intel Core i5 and AMD Ryzen 5 processor, 16 GB DDR4 RAM, 1 TB Gen 5 NVMe SSD, and a 100 Mbps broadband connection. A practical mid-range configuration. On the software side, the front end is built with React.js, Tailwind CSS, and Recharge. The backend module uses diffusion modules with VAE for generation, TGNN for graph intelligence, stable baselines 3 for reinforcement learning, heterogeneous graph transformer for threat attribution, and transformer-based sequence modeling for attack progression forecasting. Module 1. Generative Honey Token Factory, the VAE encodes real credential patterns into a structured latent space. The diffusion model then reconstructs realistic looking tokens from this representation, while adversarial training ensures they remain nearly indistinguishable from genuine credentials. This module achieves 90 to 95% of structural similarity with real credentials. Attack behavior graph intelligence. System logs are converted into temporal graph sequences. The TGNN learns dynamic relationship. This module identifies multi-stage attacks with 90 to 98% detection accuracy and provides graph-based breach visualization with anomaly scoring. Module 3. Reinforcement learning agents observe the system state and receive rewards whenever an attacker interacts with the honey token. The SAC algorithm continuously refines its policy to learn the most effective placement strategy, achieving 85 to 96% strategic effectiveness. Module 4. The HGT models complex relationships between users, IPs, tokens, and system entities. Attention mechanism learn attackers' fingerprints, while transfer-based graph sequence model predicts next stage attack transition. This module achieves 85 to 92% of attribution accuracy for forensic analysis. These are few implementation screenshots of HoneyGuard dashboard, which is fully live and functional. In the Honey Token Factory screens, we can see tokens being generated in real time across multiple types, JWT tokens, API keys, database credentials, and cloud API key. Each generated tokens displays its entropy score, authenticity score, and discriminator score. For example, a JWT token showing 95% of authenticity with an entropy of 5 means it is nearly identical to structure to the real token. The deploy screen shows the reinforcement learning recommendation engine in action. The active deployments list tracks all live track endpoints in real time. The live monitor screen is particularly impressive. It shows real-time attack feeds with GET requests hitting trap endpoints, anomaly timelines, and the current threat level reading 0.990 marked as critical. The alert screen shows 15 total alerts, 5 critical and 10 high across 5 unique IPs. The attack map provides real-time geolocation of attack origins plotted on a world map. For the time being of the project, we simulated the attacks since private IPs cannot be geolocated. The breach reports screen auto generates downloadable PDF intelligence reports. And also the prevention module, we have block IPs and prevention law. All research references are drawn from IEEE transaction on network and service management, IEEE transaction on dependable and secure computing, scientific reports, Internet of Things Journal, and other peer-reviewed publications covering intrusion detection, IoT security, federated learning, and cyber deception techniques. HoneyGuard is fully functional AI-driven cyber deception system. It generates realistic honey tokens, deploys them intelligently using reinforcement learning, detects attackers in real time through graph intelligence, attributes threats accurately, and generates forensic reports automatically, all in one uniformed platform. Thank you so much for watching, and I hope this gave you a thorough understanding of what we have built. Thank you.